Welcome back to The Explainer. Today, we're diving into something that honestly feels straight out of a sci-fi movie, but it's happening right now in the medical field. I want you to imagine a robotic arm operating inside a human body. It is an incredibly high-stakes environment. But here's the wild part. Sometimes the robot doesn't exactly know where its own tools are. I know, it sounds crazy, but tracking shiny, featureless metal instruments inside a messy, dynamic human body is just notoriously difficult for artificial intelligence. Without textures or patterns to lock onto, traditional cameras are essentially blind. So today we're exploring a completely groundbreaking solution to this problem, a system that literally tracks the untrackable and is paving the way for true autonomous robotic surgery. Okay, let's dive into this. Here is our roadmap for how we're going to break down this fascinating research. First, we'll look at the robotic surgery challenge itself. Then, we'll uncover the data shortage problem. From there, we'll explore SurfSurg6D, a synthetic solution, and the SurfSurg6D algorithm for smarter tool tracking. Finally, we'll look at the results and discuss the future of surgery. All right, part one, the robotic surgery challenge. Let's set the stage here, because the stakes literally could not be higher. We are talking about minimally invasive procedures where absolute millimeters matter. Now, to automate, or honestly, even just to effectively monitor these procedures, the system needs what we call surgical instrument pose estimation. Simply put, this is the ability to accurately determine the real-time 3D rotation and translation of surgical tools during a procedure. Let's break that down. Translation just means finding the exact X, Y, and Z coordinates in physical space. Rotation means determining the pitch, yaw, and roll of the tool's tip. Think of it like a highly precise GPS, but instead of navigating roads, it is navigating a 3D tunnel inside the human body. An automated robot desperately needs these exact coordinates for safety, for assessing a surgeon's skill, and eventually for semi-automated surgery. Without this 3D GPS, the robot is flying blind. Section 2. The data shortage problem. So, if we need this GPS so badly, why don't we have it working perfectly yet? Well, that brings us to the main roadblock. It turns out, the operating room is an absolute nightmare for AI. Let's look at the villains of our story here. First, you might think, well, just use depth cameras. But hardware sensors are bulky, making them completely impractical to fit into the tiny incisions used in modern operating rooms. Second, the data we get from the robot's own internal cables, its kinematics, is highly unreliable because those internal cables physically stretch and bend during a long surgery. Third, just look at the tools themselves. They're mostly shiny, reflective metal with zero distinguishing textures. To a camera, it just looks like a blinding glare. Fourth, the camera view is frequently occluded, blocked by splashing blood and shifting tissue. And finally, because of all this chaos, there is a massive shortage of accurately annotated real-world surgical images to actually train an AI on. General AI models completely fail here because they've just never seen anything this messy. Now, what's really interesting about this slide is how it reveals a massive gap in the field. When you compare historical datasets, you see that previous ones like SurgeRipe or Endovis either had very few images or they completely lacked the crucial 60 pose annotations, that exact 3D rotation and position data we were just talking about. And there's a good reason for that. Human annotators simply cannot accurately guess a perfect 3D angle from a flat 2D medical image. Trying to manually tag thousands of surgical frames with millimeter precision is practically impossible. But the researchers behind today's paper created something called SurfSurg6D. It boasts 60,000 images, uses complex RGB and depth data, and crucially, has perfect 60 pose annotations. The catch? It is entirely synthetic. Until now, no massive dataset existed that provided both this kind of scale and absolute millimeter accuracy. Section 3. SurfSurg6D. A synthetic solution. Since getting perfect real-world data is basically impossible, the researchers did the next best thing. They built their own perfectly accurate reality. They built a rendering pipeline that's almost like the Matrix, procedurally generating over 60,000 flawless training images. Here is how they did it in 3 steps. Step 1, background extraction. They took real video from endoscopic surgeries and reconstructed highly accurate 3D mesh models of actual tissue environments. Step 2, conditional pose sampling. They digitally placed 3D models of surgical instruments right into these fleshy backgrounds. But, and this is key, they applied real robotic motion constraints, so the tools only moved in physically possible ways. They intentionally filtered out any impossible collisions. This is absolutely vital, because if an AI trains on an image of a tool just glitching through a virtual organ, it learns bad physics and will fail in the real world. Step 3, light randomization. They constantly altered the light location, direction, and intensity for every single frame to mimic the chaotic dynamic lighting of a real surgery. So the AI is fed this incredibly rich, multi-layered understanding of the environment. It doesn't just get a flat picture. We have the standard RGB image, what the human eye sees. Then there's the depth map showing exactly how far away everything is in space. There's also a perfect segmentation mask isolating exactly where the tool parts are from the background. And crucially, it generates a normal map, which mathematically defines the precise curves, slopes, and angles of the tool's surface. This combination provides the AI with a deep geometric understanding of the space, rather than just a collection of colored pixels. And this is exactly why those constant randomized variations are so critical. By constantly shifting the background tissue, swapping out different instrument types, and dramatically altering the lighting across every single frame, the researchers literally force the AI to learn the actual physical shape of the tool. It can't just cheat and memorize a specific shadow or weird patch of shiny background tissue. It has to truly understand the geometry of the instrument to find it. So, you might be wondering, we've solved the data problem by creating this perfect synthetic training ground. But that leads us to the next massive question. How do you actually teach an AI to track a shiny, featureless piece of metal, even when you have the data? Part 4. SurfSurg6D. Smarter tool tracking. This is where we introduce the real brain of the operation. And this brilliantly illustrates how the custom-built SurfSurg6D algorithm works. It approaches this by essentially playing a massive game of connect the dots between a flat image and a 3D model. Instead of just guessing the pose from the whole image, the model learns to correspond a single 2D pixel from the camera view to a specific 3D coordinate on the surface of the instrument. An image recognition network looks at the picture and predicts a complex mathematical signature for each pixel. Meanwhile, the system utilizes an instrument latent field. Think of this as a mathematical 3D blueprint stored perfectly in the AI's memory. The AI uses contrastive learning to match the flat 2D pixel signature to the exact corresponding point on its perfect 3D twin, giving it unmatched spatial awareness. But they made this matching process so much smarter, using two really clever techniques. First, hard negative mining. Think of this like a teacher giving students the trickiest possible practice questions. The AI is forced to distinguish between parts of the tool that look visually identical, like two smooth, shiny pieces of metal, but are geometrically far apart in 3D space. This accelerates its learning and vastly improves precision. Second, consistency regularization. This ensures the AI understands the true 3D shape as a rigid object. When the AI gets confused by reflections, it might try to mathematically fold the surface of the tool in its memory just to make the math work out. This regularization acts as a strict rule that says, no, this is solid metal, it doesn't fold, ensuring the AI keeps a rigid, logical 3D map in its mind. Part 5. The results are in. We have the synthetic data, we have the super smart tracking algorithm. Now, let's look at the hard evidence proving this two-pronged solution actually works. So the crucial point here is what happens when you stack it up against baseline models. The data really speaks for itself. We measure success by looking for lower numbers in rotation error and translation error and higher numbers for the 80-10 metric. SurfSurg6D just outperforms all the competitors across the board. It hits the lowest rotation error at 6.59 degrees and the lowest translation error at 2.63 millimeters. But let's look closer at that 80-10 metric, where it hits 47.46%. 80-10 is incredibly important. It measures the percentage of AI predictions where the position error is less than 10% of the instrument's total diameter. That is a wildly strict benchmark for precision, and hitting the highest score here proves it is demonstrably better at knowing exactly where that tool is in physical space. Visually, the difference in accuracy is stark. Notice the axes plotted over the tools here. These solid red, green, and blue arrows represent the ground truth, the actual, factual position of the tool. The dashed arrows represent the AI's prediction. On the top, with our new SurfSurg6D model, the dashed arrows lock tightly onto the solid ones. It knows exactly how the tool is angled. But look at the bottom, with the older model. The dashed arrows drift significantly. The older AI literally thinks the tool is twisted when it isn't. And it gets even more impressive when things get truly messy. Look at how the models handle severe occlusion and reflection. Even when the instrument is heavily occluded, buried deep in tissue, or blown out by blinding glare bouncing off blood, the new model stays locked on. The older baseline model is completely thrown off by the glare and the blood, with its prediction arrows pointing entirely the wrong way. That hard negative mining strategy we talked about earlier is exactly what keeps our new algorithm from getting confused by shiny metal reflections. Plotting the actual joint tracking points reveals the true leap in performance. The green dots are the absolute ground truth locations on the instrument. The red dots are our new model's predictions, and the yellow dots are the older model. Notice how tightly the red dots hug the green ones, landing perfectly on the mechanical joints of the tool, while the yellow dots are just drifting off into space. This proves a huge point. This model successfully generalizes. It learned from perfectly clean synthetic training data, but it can take that knowledge directly into messy, real-world clinical footage and still track with incredible precision. Section 6. The future of surgery. We've seen how this technology works and how effective it is, so let's shift focus to what this breakthrough actually means for the medical field going forward. Let's move on and see how this builds, because solving this tracking problem is really just the first domino to fall. The researchers outlined the next massive steps. First, recovering the full articulated configuration, meaning tracking every single moving joint, cable, and angle of the instrument all at the same time. Next is developing lightweight temporal tracking modules. This right here is the holy grail of surgical AI. It means making the AI so computationally efficient that it can process 30 to 60 frames per second on live surgical video streams without any latency. Obviously, if a robot is going to assist in surgery, it cannot make a move based on outdated data from half a second ago. This ultimately leads to real-time error detection and advanced surgical skill assessment, where an AI can review a surgeon's exact micromovements to help them improve. Which brings us to a final, profound question. We are watching AI conquer one of the messiest, most unpredictable environments imaginable. If AI can accurately track the untrackable in the dynamic, chaotic environment of a human body today, well, how soon until it safely takes the scalpel itself? Because this research isn't just about drawing boxes on a screen. It is the foundational spatial awareness required for the inevitable progression from AI observation to true robotic surgical autonomy. Thanks for joining me on this explainer, and I'll see you in the next one.